let's continue with our next talk by Xavier Tolsa, who is going to talk about Riesz transforms and the Painlevé problem.
All right. First of all, I would like to thank the organizers, especially Javad, for inviting me with this talk in this workshop. So thank you. So this is a joint work with Damian Dombrowski, who was my PhD student a few years ago. Well, he finished last February, his PhD. Right. So, well, here there is some acknowledgement that I am obliged. Let's go on. And then we start with some definitions. Well, first, let's say that my talk will be not about complex analysis, but well, the motivation, we can think that it stems from some problems that by now are more or less well understood in the complex plane. And then we are trying to extend these results or to understand the similar results in higher dimensions. So I apologize for that. All right. Yeah, we will be in all the talk in Rn+1, right? And then in all the talk, mu will stand for a Borel measure in Rn+1. And typically these measures are n-dimensional. So you can think, if you want, that mu is equal to n-dimensional Hausdorff measure on some set with finite Hausdorff measure. So remember that n-dimensional Hausdorff measure is n-dimensional volume. So for instance, in the complex plane, you could have some measure which is arc length on some set. But we will deal not only about these measures, but about much more general measures. But these ones are some that are particularly interesting. All right, then I start with the definition of the n-dimensional Riesz transform of a function, locally integrable with respect to mu. So this is defined by this. Well, this is written by Riesz transform with respect to mu of f in the point x, and this is the limit as epsilon goes to 0 of this integral. This is the singular integral associated to the Riesz kernel of homogeneity minus n, right? So we are in Rn+1, and then the homogeneity of this kernel is minus n. And then we have this epsilon truncation, and we integrate f with respect to mu. And the analogous object in the complex plane is the Cauchy transform. So the Cauchy transform is defined by the limit as epsilon goes to 0 of the epsilon truncated Cauchy transforms. That notice that here I wrote x and y. X and y are complex numbers. So this is not the standard notation, but I wanted to write this in this way so that these kernels look pretty much the same. So in fact, this kernel and this kernel in the complex plane, they are the same up to a conjugation. So the study of the Cauchy kernel or the Cauchy transform in higher dimensions would consist in studying essentially this Riesz transform, or at least this is a possible generalization. All right. Let me say that although we define the Cauchy transform taking this limit and the Riesz transform taking this limit, the existence of these principal values is a very delicate question, and a priori this is not guaranteed. And for this reason, then we say that the Riesz transform is bounded in L2 mu if the truncated operators, these ones here, are uniformly bounded in L2 mu uniformly on epsilon, and the same for the Cauchy transform. In this way, we don't have to talk about principal values. Then an important question is this one: for which measures the Riesz transform is bounded in L2 mu? So the idea or the problem is to characterize in a metric or geometric way such measures. And why this is interesting? Well, because this has applications to the study of the removable singularities for Lipschitz harmonic functions. This is the so-called Painlevé problem for Lipschitz harmonic functions. And in the case n equal 1, that is in the complex plane, then this would be related to the study of removable singularities for bounded holomorphic functions. We will see later something more about this. Also, one may expect some applications to the study of harmonic measure if we obtain results in this about this characterization of the measure such that the Riesz transform is bounded in L2. Because in the last years there have been many advances in the study of harmonic measures in higher dimensions, and in some of them the connection between the Riesz transform, harmonic measure, and rectifiability played an important role. All right, yeah, and I have just mentioned that there is a connection to rectifiability. So this question, in fact, is connected to rectifiability. And so let us now see what is rectifiability for us. So we say that a set E in Rn plus 1 is rectifiable, or one rectifiable if you want, if it is almost everywhere contained with respect to this measure, that is a one-dimensional Hausdorff measure or arc-length measure, if it is almost everywhere contained in a countable union of curves with finite length. Some people call this notion, instead of rectifiability, countably rectified or countably rectifiability, or they say that the set is countably rectifiable. That's it. And then in higher dimensions, or sorry, in higher dimensions. Well, this set is one rectifier, but it could be contained in the complex plane, but also in this notion of one rectifiability makes sense for sets in Rn plus 1. Anyway, we say that a set E is n-rectifiable if it is almost everywhere contained with respect to this Hausdorff measure, the dimensional one, contained in a countable union of C1 or Lipschitz and dimensional manifolds. Here I put C1 or Lipschitz because up to sets of 0 and dimensional Hausdorff measure, we get the same. So the definition is equivalent, can be stated in terms of C1 or Lipschitz. All right, so we have seen what is a rectifiable set. And then what is a rectifiable measure? Well, we say that E is n-rectifiable if it is of this form. It is G, function G, times n-dimensional Hausdorff measure on a set E that is n-rectifiable. So this measure is absolutely continuous with respect to n-dimensional Hausdorff measure, and moreover, it is concentrated on a set that is n-rectifiable. All right. So the notion of rectifiability that we have just seen is a kind of qualitative. It is good for some purposes. For instance, it is stable by countable unions, but for other purposes, like more quantitative, it is not so good. This is the reason why some people, well, these people were in fact the Wittgensteins, introduced the notion of uniform rectifiability. So first, we define irregular measures. So we say that a measure mu in Rn plus 1 is irregular, or Alford-David regular, if the measure of each ball centered in the support of the measure and radius up to the diameter, the measure of these balls is comparable, the measure of the ball comparable to the radius to the power n for each of these balls. All right. Automatically, if this condition happens, by the way, the measure then is comparable to the n-dimensional Hausdorff measure restricted to the support of the measure. All right. So then this is the notion of irregularity, and then we say that measure mu is uniformly unrectifiable if this thing here. So if you are not very familiar with this notion, don't worry too much, because you essentially you have to understand that this is a uniform unrectifiability is a quantitative version of rectifiability. Anyway, I would say that the measure is uniformly unrectifiable if it is irregular with this exponent n, and there are two constants n, m and theta, such that for all x in the support and for all radius up to the diameter of the support, for this x and r, there exists some Lipschitz map, some mapping that goes from this ball contained in Rn to Rn plus 1, that it is Lipschitz, so with control Lipschitz norm, with this m, so that the ball Bxr contains a big piece of the Lipschitz image of this ball B sub n by the map G. So the measure of this ball intersected with the Lipschitz image is bigger than some constant theta to the power n. So notice that because of the irregularity, we have that mu Bxr is comparable to r to the power n. So in fact, then this thing here at the end, under this condition, is comparable to r, this, right? Because all right, because the upper estimate is a consequence of this one, and then the lower comes from this. All right. So, well, uniform unrectifiability is, as I told you, is a quantitative version of unrectifiability introduced by David and Sims in order to study the L2-boundedness of singular integrals and in some sets in the Euclidean space, and also to study other problems like removability for Riesz's harmonic functions, or for complex for holomorphic functions in the plane. Then here we have some answers about the question for which measures the Riesz transform is bounded in L2. And some answers were known up to now in the case when the measure is irregular. So when the measure is irregular, the Riesz transform is bounded in L2 mu if and only if the measure is uniformly unrectifiable. The fact that the measure is unrectifiable implies L2-boundedness was shown by David and Sims a long time ago using harmonic analysis, using the L2-boundedness of the Cauchy transform on Lipschitz graphs, etc., and many other tools. The converse direction showing that the L2-boundedness of the Riesz transform implies uniform unrectifiability is more difficult. You can think of this as some kind of free boundary problem. We start from some analytic condition, and we have to prove a geometric one, right? And in the case n equal 1, this was shown by Matila, Melikov, and Verdera, and for n bigger than 1, this was shown by Nazarov, myself, and Wolberg a few years ago. Remember, by the way, that we're always talking about the Riesz transform of codimension 1, Rn plus 1. So it's and so that the case n equal 1 corresponds to the Cauchy transform. And a few words about the case n equal 1. In the case n equal to 1 in the plane is easier than the case of higher dimensions, because we can use what is called the curvature of measures. So the curvature of a measure is defined in this way. First, we consider 3 points x, y, z in the plane, and we consider the circle that or circumference that passes through the 3 points, and here we have the radius of the circumference. then the curvature of mu is this triple integral here. So we have the triple integral of 1 over this radius of this circumference that passes through the 3 points squared, and we integrate 3 times with respect to the measure. So if the 3 points are aligned, we assume that the radius is equal to infinity, and then this quotient here is equal to 0. So in a sense, the curvature then measures how flat is the supportive the measure, probably something like that, right? Because in a sense, this, for instance, when the curvature is 0, it is almost trivial to check that then the measure is supported on some line. All right. So why is curvature important in connection with the Cauchy transform? Well, because of this formula found by Melikov and Berdera. They show that if when we have a measure with this upper growth condition, so we don't ask mu to be irregular, but just the upper growth. Then if this condition holds for all balls, because we have here all points and radius, then the L2 norm squared of the Cauchy transform of the function 1 is exactly equal to 1 over 6 times the curvature of mu plus some error term. And this error term is bounded by the total, I will write it here, this error term, well, is just, of course, by definition of the notation, if it's bounded by this. We have to think about measures with that are finite. And this constant here depends on this constant here. Well, this formula, by the way, was preceded by a result due to Melikov that connecting the Cauchy kernel to the Menger curvature of 3 points. That is, he had a discrete version of this formula, let's say, before. All right, then notice that if the Cauchy transform is bounded in L2, then this thing here will be bounded, right, by the total mass. And we assume that the measure is finite again. And then we'll have that the measure, sorry, that this will be bounded. And so the curvature then will be bounded because this zero term is bounded. So then we can connect the L2-boundedness to something that is kind of geometric or metric and geometric, that is this curvature. All right. In fact, applying some harmonic analysis, applying the T1 theorem, one can show that the Cauchy transform is bounded in L2 if and only if we have this upper growth condition. This is rather easy, and then we have this condition on the curvature of the measure. This is very in going from this direction to this is almost trivial when you have this formula. We only have to apply this formula to the measure restricted to the ball B. Going to the other direction is, for that we have to apply the T1 theorem. All right, so this formula and this characterization of the L2-boundedness of the Cauchy transform is interesting because it has applications to analytic capacity, and moreover, this condition is stable by Lipschitz mappings. We'll see a little more about this later. And what happens in higher dimensions? In higher dimensions, we don't have any formula similar to this one. And it seems that it's essentially impossible to get anything like this. Of course, one can define some kind of curvature in higher dimensions, but to connect this curvature or this possible curvature with the L2 norm of the Riesz transforms, this cannot be done in this way. This was shown by Farag. He had some precise statement of this form. So in higher dimensions, then we use more complicated techniques. Then what is our main result? Let's go to that. For a ball BXR, we denote by theta sum mu of this ball, this or theta sum mu of these points, this average density. So the density is the measure of the ball divided by the radius to the power n. And then we consider this coefficient, beta coefficient that measures the flatness of the measure. So this is equal to the infimum over all n planes of this quantity here. So we have 1 over r to the n, and we integrate on the ball. And here we have this distance, y to 12 divided by r squared, and we integrate with respect to mu. And then we erase. So notice that what this coefficient does is to, let's do a drawing here. Yeah, is to imagine that we have some measure that is lives in this black lines, and then what we are doing is finding a plane that, in a sense, minimizes these distances here, quantified in this L2 way, right? Because we are taking the infimum over all these n planes, and we are measuring this distance here. So, for instance, if some measure inside, if a measure inside this ball BXR is concentrated in some n plane, then of course this coefficient will be 0. So this coefficient measures the flatness of mu inside that ball in this way. All right, and one moment. No, sorry. So our main theorem is this one. So given an arbitrary measure in Rn+1 with no point masses, the case of when the measure has Dirac deltas, this is there are some kind of pathological phenomena that are not interesting for us. And then for this type of measures, arbitrary with no point masses, the Riesz transform is bounded in L2. Oops. The Riesz transform is, I'm one moment. I wanted, sorry. Here, I wanted the pointer. All right. So the Riesz transform is bounded in L2 if and only if we have this condition where here we are saying that the density of any ball is bounded by 1 or by some constant. So this is the same as saying that the measure of this ball is bounded by some constant times its radius to the power n. And moreover, we have this condition that essentially is the most important one. This is a square function that involves this coefficient here squared, so that then this square will be cancelled with this, and then these coefficients are multiplied by the density. We integrate with dr over r, and we multiply by mu. So it's a square function involving the betas coefficients squared with this. Notice that here we are integrating from 0 to this radius, dr over r, and here we have this. And this must happen for all ball play. So you can think that this is perhaps a little involved condition, but the important thing is that this is essentially geometric in the same way as curvature. So the Riesz kernel involves has some cancellations. It's not a positive kernel, but this square function involves only positive things and with geometry. Here I stated the theorem again. Well, the proof of this theorem was obtained by Dombrowski and myself for measures satisfying an appropriate Wolf condition. And then later, the general case was obtained by myself. So in fact, the result consists of 2 papers. Let me say also that the case equal 1 of this theorem, of this characterization of the L2-boundedness of its transforms, had been obtained in this way by Jonas Assam and myself some time ago, using the connection with curvature. So remember that in the case n equal 1, one can characterize the L2-boundedness of the Cauchy transform using curvature. But here what I say is that in the case n equal 1, the same formula is also true. And this is the result that I am stating here. All right, the implication, the fact that when this condition is satisfied, and this one, when these conditions are satisfied, then we have L2-boundedness. This was proven by Girela-Sarrión in his thesis a few years ago. Girela-Sarrión, by the way, is the son of the preceding speaker. All right, so let's continue. Then the fact that this this condition holds was proven also under stronger assumptions for assuming that all Calderon-Simon operators without kernel are bounded in L2, not only one kernel. This also holds. But in this case, this result holds not only for the case of codimension 1, but in higher codimensions. And this was shown by Benjay, Fejam Nazarov, and myself also a few years ago. So now I state a few consequences of this theorem about Riesz transforms and the beta coefficients. First, it turns out that the Riesz transform controls the L2-boundedness of all other singular integral operators with a smooth n-dimensional Calderon-Simon kernel. So if we have a measure in Rn+1 with no point masses, applying the previous theorem and other collateral results, one gets that if Riesz is bounded, then all singular integral operators with odd n-dimensional Calderon-Simon kernel is smooth enough, let's say C2, then these operators are bounded in L2.
Hello? Yes, Vasily.
Sorry, can I continue?
Ναι.
All right, well, I continue.
Όλο το χωριό εκεί.
Someone needs to mute all their things here.
All right. So then another corollary is this one. So if we have again a measure with no point masses, then if we have a Lipschitz map from Rn+1 to Rn+1, then we consider the push forward measure or image measure of mu by phi, and it turns out that if the Riesz transform were bounded in L2 mu, then the Riesz transform with respect to sigma is bounded in L2 sigma, and we have these bounds for the norm. So the condition of L2 boundedness is stable by Lipschitz mappings, and this is something quite strong, because even up to now this was not even for affine invertible maps. So notice that, for instance, in the case of the Cauchy transform, it is very far from being trivial that the same condition holds, because just notice that the Cauchy kernel is connected to analyticity, and holomorphic functions are not stable even for affine maps, right? So then, and the same happens in higher dimensions for harmonic functions, let's say. All right. Then another consequence is that if we have a Lipschitz mapping, then a set is removable for Lipschitz harmonic functions if and only if the same happens for the Lipschitz image of the set. This was already known in the case of the plane for analytic functions using curvature. This had been proved by myself in 2004 or something like that. All right. We say that is removable for Lipschitz harmonic functions if for any open set omega that contains E. If we have a function that is harmonic and Lipschitz here in omega minus E, then F extends harmonically to the whole set omega. So the analogous notion for bounded analytic functions is that is removable for a bounded analytic function if we have a set such as this, omega and t in the complex plane, if f is bounded and holomorphic in omega minus z, then f extends analytically or holomorphically to the whole omega, right? So, for instance, a point by the classical Riemann theorem is a removable singularity in the complex plane for bounded analytic functions. Also, it is easy to check that sets with zero length are removable for bounded holomorphic functions. All right. But the characterization of this removability is something delicate. It is the geometric characterization is called the Painlevé problem, and it involves rectifiability and other things. So, but let's go on because this is not the main topic of the talk. Here, I will go very fast through this slide. You don't have to read all this. Just here it is written that if you are familiar with analytic capacity, the analytic capacity is a notion that is used to measure how non-removable is if a set, and also appears in problems of rational approximation in the complex plane. And then the analogous of analytic capacity in higher dimensions is the Lipschitz harmonic capacity denoted by kappa of V. Analytic capacity can be characterized using curvature of measures, and Lipschitz harmonic capacity can be characterized in this way. So it's let's say is a way that involves densities and this square function that I wrote before, but don't pay much attention to this. Maybe it's too much information for now. But let's say only that also this capacity, in the same way as analytic capacity, is stable by Lipschitz mappings. We have that kappa of V is comparable to kappa of phi of V. And the comparability constant only depends on the by Lipschitz constant. All right. So all these results were consequences of this theorem that is again written here. And now I will talk about the proof of this theorem. It's a very long proof, 2 papers in fact. So I will talk a little about the sketch, about the scheme of the proof, and the scheme of the proof, or the strategy. So the first, we prove this theorem that can be considered as a particular case of the preceding one. That is the joint one with Dombrowski. So here is the same. Well, it's a very related theorem, but it is it contains an important extra condition that is with one. So here we have a radon measure in Rn+1. Radon means Borel-and regular, such that it satisfies this growth condition for all x and r. This is the same as saying that the density of any ball is bounded by some constant. And we assume that for any doubling cube, this condition holds. And what is a doubling cube? Well, a doubling cube is a cube such that the measure of 2q is comparable by the measure of q. And this the mu, you can think of this if you want about as some lattice associated to the measure mu. Then and what is this theta mu of q? This is equal to the measure of, this is the density of this. This is mu of p divided by Lp to the power n. So if we have this condition here that involves these densities squared and multiplied by measure of p. So notice that we are summing over all p's, all cubes p contained into q. Then we have this, and then we ask this thing to be bounded by this. And then we have this factor here that in a sense penalizes the fact, well, it depends on penalizes or as you prefer, the fact that LP goes to 0. So when LP goes to 0, this term, of course, goes to 0. So if this condition holds, then we have that this square function involving the betas and the densities is bounded by the Autonoma of the Riesz transform plus the total mass. And here a few comments about this again. The way to understand this condition, well, in fact, this is a technical condition. You can, but notice that, for instance, when the measure is irregular, the densities, all of them are comparable to 1. So when the measures are comparable to 1, then this inequality is satisfied, because we'll have, when this is 1 and this is 1, we will be summing over all cubes P contained here into Q, but this factor here makes the sum to be convergent. So this condition is satisfied for irregular measures, for instance, right? So then, in a sense, this condition prevents of having a high oscillation of the density. That is, if the density of the cubes P, for instance, becomes very high or very big when we go to smaller and smaller cubes. Imagine that, for instance, we can have a measure and we can have a Dirac delta. Let's say here a Dirac delta. If we have a Dirac delta, then when we compute the measure of or the density of this cube, maybe it will be small, but when we consider smaller and smaller cubes, this density will go to infinity. So such phenomena are forbidden for this fact. Well, by the way, this measure cannot have point masses, so Dirac deltas do not appear. But instead of a Dirac delta, think just as a measure such that we have a lot of measure concentrated close to some point, let's say. All right. So let's go on. So then, in fact, instead of proving besides proving the preceding theorem, in this paper with Damian Dombrowski, what we do is to precise a stronger result that involves what we call the high energy cubes. The high energy cubes are the family of doubling cubes such that the condition in the previous slide was not satisfied. Remember, in the preceding slide, we asked this to hold, this condition to hold, right? So here we are saying that, okay, don't assume that condition. Then instead of that, consider the cubes that violate that condition, right? And then define this by or denote this by energy of Q, or big epsilon of Q. All right. Then what we prove in that paper is that this square function involving the beta coefficients is bounded by the square of the Riesz transform, the Autonoma of the Riesz transform applied to mu. By the way, I'm not sure if I think I didn't say. Maybe you already know, but the Riesz transform applied to the measure mu, of course, is the Riesz transform of the function 1. So then we have that this thing is bounded by this, plus the energy of these bad cubes. So the bad cubes are the ones with high energy and are the ones for which this is very big, right? We have this. All right, and then the second part of the proof is the theorem by myself alone, that where I showed that this condition holds. So when we have a measure with this growth condition, then these energies of the bad cubes are bounded by the this L2 norm plus this. So notice that now if we gather this and this, we'll have that this term here is also bounded by this thing plus this, so that we get that this integral here is just bounded by these two things, right? Because this term here is bounded by this. And so this is the strategy of the proof. Then, okay, and then I will go pretty fast about this because I think it's not worth looking at too many details. But the general scheme of the proof, I will talk only about the proof of the first result, the one with Dombrowski. So the idea is to decompose the Riesz transform into martingale type operators. We're using these martingale type operators or differences, and this is a technique very common in harmonic analysis. So this delta q of this function R mu is the sum over the children of q. So these are dyadic cubes, and here we put the mean over p of this function in the cube p in the sum, and then we subtract the mean over q of q is the parent, is the parent, right? So we have a q, and then we have the sums here. This is a cube p. All right. So this is this function, and then it turns out that these functions delta q R mu are orthogonal each other. This is very easy to check, and in fact, one can show that by orthogonality, the square of the L2 norm of these functions, of this function, the Riesz transform of mu, is equal to the sum of these squares of the L2 norms of these functions, the delta q. In fact, this is expansion. In fact, we have this comes from, of course, from this. This comes from this fact. This comes, of course, from because we have. Oh, sorry, it's written before. We don't have. It's written here. This comes from this, and plus orthogonality. And let me say that this expansion is analogous to the expansion into hard wavelets. It's essentially the same. Then remember that this is what we want to show, right? This is what we want to show. I wrote it here. And how we show then what? Well, what we do is we decompose the dyadic lattice into a family of trees. So a tree of cubes is just we have to think as the structure of dyadic cubes into in this way, right? So it's so that some descendants of some cube are make some tree. All right. So and then we can organize. What we do is to organize we partition the dyadic lattice into some family, countable family of trees with root Ri. Yeah. Sorry, with roots. This is the root Ri, and so that for in each tree, the density is stable. The density of each cube in each cube here inside the tree is comparable to the density of the root. Ri is the root. Is the starting cube of the tree? Is there? All right. Then what in this tree, since the density is stable, we have that essentially you can think that the measure behaves as if it were irregular. Then using the results that are already known for the irregular case, using the description of the L2-boundedness in terms of uniform rectifiability, one can get that one has this formula, the sum, when we only sum over the cubes in the tree of these beta coefficients times the density times this is bounded by this. All right, so we have a packing condition of these beta coefficients times these densities inside the tree. Then what remains to do is to prove this. This is what we show. Then we show that, and this is a difficult step. What we do is to prove that when we sum over all the roots in the tree, only over the roots, this density is square, we have this bounded by this. And notice that if yeah, one moment, what I want to say, yes. First, why we want to show this? Well, because if we show this thing here, then when we sum over all I here and we put here over all the roots, we'll have that this thing sum here will be bounded by all these things here, right? And notice that when we, since these trees partition the same coefficients over the dyadic lattice, we will be summing everything over the dyadic lattice, right? So this is then what we want to show. And how do we show this condition here? How do we show this? Well, the idea is to show that in each tree, for each root, we have these coefficients bounded by these hard coefficients of the Riesz transform associated to the tree. Because notice that if we do this, then now let's go on. If we do this, then we will have, imagine from this condition, when we sum here, by orthogonality, we have that this is, oops, sorry, this is the, this, right? So that, I repeat, if we have this boundedness here, then we are done, because in fact, we get this condition and plus these things, but these things here that appear in a sense are some kind of error terms. All right, so then the idea, as I told you, is to show that for each root, we have this. And then a very fast thing, let me say that in fact, this is the naive approach to show that in each tree where the density is stable, we have that. But in fact, this is not what we do, but instead of that, we show that for some selected family of trees. And that selected family of trees is big enough so that this sum over all roots is comparable to the sum over this selected family of trees. And this selected family of, and these trees where that are kind of selected are special because in a sense the density oscillates in such a way that we can estimate the Riesz transform from below, or the hard coefficients of the Riesz transform associated to the cubes in that tree from below. And to do that, we apply some variational argument, well, some approximating measure. We transfer that to the results from that approximation measure to the Riesz transform of mu. Then some errors appear, and the errors that appear are controlled by these energies, that make all this argument and delicate, more complicated. All right. And then for the final theorem, just say that we use, or I use as related strategy, but decomposing things into trees, which was I associate to each cube of high energy, also some trees of cubes. But the things are also quite delicate because later we have to apply some bootstrapping arguments to estimate some errors. All right, and just I finish very quickly with mentioning some open problems. First, for instance, it is not known this thing. Assume that we have, as even in the irregular case, is not known. Assume that we have a measure in Rn+1 such that the Riesz transform is bounded in L2, and that it is constant mu almost everywhere, so that it is Riesz transform of mu is 0 in the BMO sense. Then the question is mu a flat measure? That is this equal to Hausdorff n-dimensional measure on an n-dimensional plane? And this is non-knowns. If this were true, some arguments of all that strategy that I have explained, it could be simplified a lot, possibly. Also, in higher codimensions, everything is very, very open. In fact, in the results that I explained, in the variational argument that I mentioned very quickly, we need to use the harmonicity of the kernel. For the Riesz transform of codimension 1, its kernel is the gradient of the fundamental solution of the Laplacian up to constant, and so that is it's a harmonic kernel, and we have then we can use there in some of the arguments a maximum principle that plays a key role, and the maximum principle comes from harmonicity. Also, all this that I explained is absolutely open in higher codimensions. Well, except in the case n=1 is also works, because curvature also works even for one-dimensional sets in higher dimensions. And in fractional dimensions, there are related open questions. So I finish here. So thank you.
Oh, thank you so much.
Welcome.
Okay, so we're opening for comments or questions. You can either post them in the chat, and since I can't keep track of everybody, just shout out whatever question you'd like to ask.
Could you, hi Xavier, great talk. Could you give a little bit more intuition on this, I mean, selection of trees that the oscillation, I mean, the density oscillates a lot?
Yeah.
Because you said you could estimate from below the...
Yes. Yeah, I make here a drawing. In a sense, let's say that the partition that we do in the into trees is so that essentially the density is stable inside the tree. But then, of course, then we have to quantify how many times the density changes, let's say. Then what we do is to form some trees, gathering some other trees, we form other trees, and what we can estimate is the case, for instance, whether we have some tree such that in some here we have the root R. Here, imagine that these are the cubes P that are the stopping P belongs to are the stopping cubes. And here, let's say that we find some cubes, with some intermediate cubes, such that the density in these intermediate cubes is larger than the density of R, and then smaller than the density of the stopping cubes. Let's say that the density, imagine that goes from here. We have low density, or let's keep this cube has low density. These ones have high density. And the stopping ones have again low density. So in this case, the variational argument to estimate the Riesz transform from below works. And then one of the difficulties, well, there are many technical difficulties. One is to obtain these estimates on these trees, but then another difficulty, in a sense, is to gather all these trees, to form these trees so that they so that working in these trees is enough to get the final estimates. That is to find the selected trees so that they control all the others. So these are these are the selected trees in a sense. The ones where the density of the root is low, then intermediate layer with high density, and then again in the stopping cubes, low density again.
All right, other maybe quick questions? If not, let's thank Javier Tolsa again.
Thank you.